So welcome to the Friday seminar. Today we have Ibrahima Bah, who will tell us about aspects of topological symmetry, Branes, and holography.
Thank you for the invitation. It's quite nice to be back here. So this is sort of a work that's more or less on and off for a couple of years that I've been thinking about it, and it's part of this larger collaboration on the strength and defend symmetries from this more general categorical point of view. So to sort of the obligatory, let's see, introduction that we have. Part of this talk will be a bit retrospective, but I think that's good for some of you guys. This might be a bit nostalgic. Okay, so recently we've seen that the notion of global symmetry is being generalized in many different interesting ways, and mostly due to the observation that symmetries fit in this broader set of topological operators in quantum field theory, and that is the sort of a structure you should try to study and understand and characterize. And of course, the notion that symmetries and topology are related is not super new. Intuitively, we see this in quantum mechanics, that what we call symmetry operators are ones that commute with the Hamiltonian, so small deformations are preserved when you have symmetry operators, and there are many wonderful things why we like them. Say much about them. So a little bit more concrete, if we consider what we usually say ordinary symmetries, which are given by Gauss surfaces that are codimension 1, we have an operator. It will have some label G, and this label we'll discuss in a bit, takes value on some codimension 1 surface, and the statement simply that when I wiggle this surface, there aren't any physics that depends on it. And in particular, I get something interesting only when I cross some operator with some charge, and the thing that I should get on the other side is just the representation associated with that operator. So the label typically in that we learn in introduction quantum field theory or even earlier, we label them with some element that are valued in some group, and they multiply by the rules of whatever group that we assign to our system. Even at this level, we've seen many generalization, which is high form symmetries, P-form symmetries, where the topological operator is valued on a higher codimension set of surfaces and measure charges for extended operators. Okay, so one of the interesting things that's been happening recently, following from this notion that we should think about topological operators in general, is that from this perspective, if we want to think about diffusion rules, meaning how I multiply or stack two topological operators that are valued in some surface, the labels that we associate to them aren't necessarily groups. And in fact, what we generally should expect is if you multiply them, you should get some sum of another class of operators with some coefficient, and then you can try to constrain those coefficients in various ways. And one of the sort of perspectives that appears is that this sort of algebraic structure should fit in some fusion category, in which case these coefficients are going to be integral and positive, and this is related to having some set of simple operators or some notion of simple operators. But once you have this sort of a structure, then it allows for something more interesting, which is that if I take an operator, here it is sort of important to have a notion of simplicity, and I multiply it with its Hermitian conjugate, where Hermitian conjugate here is time reversal, orientation reversal. We do not necessarily expect to get an identity operator. We should get identity plus some other things that appear. And this is the sort of phenomena of non-invertible symmetry. It's, on the face of it, it looks non-unitary.
Is it always some kind of projection operator or some projection operator?
So the fact that you have a projection operator is exactly the thing that there are some some state that it acts where it maps it to zero. Right? That's that statement, but it doesn't have to be. I can multiply them. I can just have a sum of them. Here, this sort of perspective is, of course, not super new. In low enough space-time dimensions, this you're familiar from Verlinde lines, or the self-dual point of Kramer-Wanier duality or Ising model. The thing that has happened recently, from this point of view, is starting with some work of Yuji and then a couple of others a few years down the road, is that these sort of operators that are non-invertible could exist in 4 dimensions and higher, and we can have explicit constructions in simple theory that we can control and understand. And this is a sort of several people tell me that there's some recursion associated to this, but at least from my perspective, recently these sets of work sort of start to tell you can look for these things in higher D in a way that we understand with field theory methods. And of course, since then, there's a large generalization, there's a growing list, there are many different ways that have been discovered on how to construct, and this notion of that there are categorical structure that should emerge in QFTs, we're starting to understand from a field theory point of view why that should be the case, and so on. However, one point that, at least from my point of view, who sort of grew up with basically being fed with holography throughout my whole career, is you can ask how such a structure, how these topological operators, if I have a field theory, should emerge in the bulk, or what are the dual description of them in the bulk. And from this point of view, you can ask, can you learn anything about these structures themselves, either from a field theory side or from the gravity side, or even can you learn something about gravity itself? And I'll say something about that. From this point of view, right, things that we already are familiar with in ADS-CFD, anomaly structures, we know how they get captured by topological sectors of the bulk. And there is this notion of symmetry topological field theory, which is being used to understand how these higher categories should act on field theories. So such a notion is also seems to be baked in already in ADS-CFT and string theory, and part of this talk is start to see how to flesh it out in detail. So to sort of the idea of what we want to understand is we consider the boundary field theory. You have some operator that you insert. It could be an extended operator, but we have just some operator that we have. In ADS-CFT, we can think of this. So first, we can have some topological operator that measures some charge associated to this. In ADS-CFT, we can imagine taking this boundary operator and attach to it with some extended defect from the bulk. This could be a Wilson line that ends on it. Then from this sort of a cartoon, this linking that you have in the boundary should be thought of as trying to understand some object that links with the line that you extended in the bulk, okay? So what you would like to understand from this point of view is what are the set of things that would link with this line. Notice that the boundary operator grew a direction in the bulk, so the codimension of the topological operator have gone up by 1. So we usually say that a gauge theory, a P-form gauge theory maps to a P-form global symmetry in ADS-CFT, but here it is the picture that's actually observing is that the topological operator measured the charge has a higher codimension from that, okay, which already there is something here to sort of try to understand. So the statement is you want to know what are the set of things that would link with this line and would measure the charge. And then you also want to explain why such a things would be topological when you push them to the boundary.
We naively have expected that there would be some kind of surface. If it wasn't the topological operator, we would have expected a surface that ends on the ring.
Good. So that surface would require for me to tell you some boundary conditions to end it suitably. But you can, and that surface, you can sort of think of maybe a dragging this ring, but my claim is the ring is enough. Right? So if I forget all the dynamics of the physics at hand, and I just were to imagine this was a topological field theory in the bulk, then this linking would measure the charge of this Wilson line, and that charge of the Wilson line would be the charge of the operator in the bound.
Is it trying to have an operator defined in the bulk?
I haven't defined an operator. I just want to think about whatever that can link with this thing in the bulk. Okay, let me see if
Sorry, but the UI sub B of sigma, that's expressed in terms of bulk fields, right?
that is going to be expressed in terms of bulk fields, and I'll try to flesh this. It looks a bit counterintuitive, but it seems to be a picture that tells me what to do.
We're not assuming the boundary is two-dimensional, are we?
No. Okay. Okay, so let's try to understand this. So first, I will give an answer, and then we'll spend the rest of the talk trying to understand this answer. The claim is that, so first of all, when we do ADS-CFT, there's two perspectives. We can take some given effective sugra in some ADS, and then just try to study the bulk to boundary duality. Or, as many of us like to just start from a full string theory, where you have ADS times some internal space, and then try to study this bulk to boundary by thinking about stringy operator. From this boundary, from this sort of bottom-up point of view, these operators, you can describe them by looking at Gauss constraints of bulk gauge theories. And from the bulk, from the top-down stringy point of view, these operators are going to look like D-brane. Okay. So first, why do we expect the Gauss law to tell us anything here? So to just briefly review this statement, if we have some P-form symmetry, and we pick some, we want to do some Hamiltonian quantization, in this case, we can pick the radial direction of ADS. We do know that the Lagrangian is not going to depend on the time component of whatever gauge field we're studying. So we get a Gauss constraint, which has to be zero, where in the quantum theory, we understand this as generating gauge transformation along some constant slice here. So the Gauss law in the bulk, we can associate to it a Page charge, right? Since the Gauss law at the classical level we write it zero, so we can define a Page charge. And this Page charge can be used to actually establish what we mean by the generator as an operator that generates gauge transformation on some slices. And just by then considering a set of transformations which are singular, you can actually define a genuine operator, which is exponential of the Page charge, at least naively, as being something that could be a candidate for what this thing is. Okay, so in this case, if this was some sort of a Wilson line, then the exponential of the Page charge would measure the charge associated to the such and such. This is, of course, a little too naive from the fact that, as that is known, if I express the Page charge in general, it's not a gauge invariant or globally well-defined thing. But what you can do is you can take this surface, but instead couple this current or this Page charge with some boundary mode on the operator in some suitable way that you recover something that is gauge invariant. Roughly, when this isn't gauge invariant, you can sort of understand it as some bulk anomaly inflow that you need to cancel, right? And then you can use some boundary degree of freedom to do that. So just this sort of cartoonish picture, once you compute the Page charge and you turn on some boundary mode on this to cancel whatever anomaly type features you have, you can construct a gauge invariant and globally well-defined operator. And whenever you do this, this actually seems to also lead to non-invertible symmetries.
Same as saying that, let's say you have a zero form symmetry in the boundary.
Yeah.
Then in the bulk you have a gauge field, and now you're using the generator of a one-form symmetry in the bulk.
Yes. So it's the equivalent picture that actually, if we have an electron and we measure the charge of an electron, we measure it at a fixed time by taking a Gauss surface, which is a 2D surface. But that surface, we should actually think of that as a one-form symmetry associated to the electron, which tracks a line in the full 4 dimensions. Right. So the global charge that measures the charge of an electron is actually a one-form symmetry, not a uniform symmetry from that perspective.
I'm a little confused because in the bulk, this one-form symmetry is not supposed to be a global symmetry. It's supposed to.
Good. So in the full quantum theory, it's not supposed to be a global symmetry, but in the very low supergravity, if I can construct this phase charge and it's closed, and it is there, and I will comment on this later. And that is I think, and that actually leads to some, I think, interesting lessons, which I will say something about. Good. So to go to the other side, why should I expect associated D-branes or branes in general to such an operator that I want is the following statement is that now if I take D-brane, which I do not end on the boundary, but I try to hold them somewhat parallel to the boundary, I can ask what is the effective theory on the D-brane. There is in general a tension of the brane, and the pullback of the metric on the brane is going to give you some R to the P scaling of the brane tension. And this sort of a feature here, what it does is that you have an effective tension on the brane, and when you push it near the boundary, the kinetic terms decouples or the degrees of freedom, the dynamical degrees of freedom freeze, so the brane becomes very stiff. The part of the data that survives, that makes it then to the boundary is the Westhamino term, which is topological. And from this point of view, if you express the Westhamino term in general, it couples non-trivially to some bulk modes for which I might have to choose some boundary condition or not, or some over them depending on the physics that I'm trying to study. But the general observation is that this will have some intrinsic dynamics coming from the Chen pattern, which is going to be topological in general. So,
question. So the operator U depended on a continuous parameter, right? At least in the case of zero form. But the branes have what would be the continuous parameter in the case of the brane?
So which continuous parameter specifically you want to think about?
Well, normally have, let's say, zero form symmetry on the boundary, and the operator U has a continuous parameter. So it's
the alpha, the e to the I alpha parameter. Right. So I will get to this point a bit later. So the examples which I will work is actually some discrete symmetry, not continuous one. The continuous one, there is something a bit more we have to think, and I can tell you about that separately. Yeah, but that's an excellent question.
But what is the claim? Is the claim that UB of sigma is a brane?
The claim is here, yes. So I want to make the claim that UB of sigma, I can think of it as a brane. It's a brane involved, right? So the continuous symmetries are trickier from this point of view. So I will work out an example where it's finite symmetries, and we can talk about continuous symmetry separately, and I can tell you.
But is there a way in string theory to directly define an object that only gives this topological part, or?
So yeah, that would just mean just extract the Westhamino term.
Yeah.
Right. And in fact, so there are two perspectives that I'm offering here. There is a phase charge, which is something we can always do, right? And then there is the Westhamino term of the associated brane. So to just, since there's questions about it, the simplest one you can imagine, just take a U1 theory, and let's just take the universal U1 in the gravity multiplet in ADS5 times some Sasaki Einstein. There actually turns out you can compute the phase charge of that. It will give you star F plus F squared, right? And F squared is coming from the anomaly term. It turns out if you take a D5 or a D3 that you put on the S1 fiber and you analyze the Westhamino term, you can recover that. you can recover that same term up to the kinetic. But there's several subtleties there, which is why I will not say much about them. Good. So, right, and then from this picture of if the claim that there are branes that does this, you can start to see why a fusion of these operators can give you something more interesting and more general to play with. Okay, so since there are questions, so let's do an explicit example and see how things work, and then we can discuss. Okay, so the example that I will try to play with is n=1 super Yang-Mills. Why is this a useful one to think about? So we have a way of thinking about this, at least in the UV, of taking ADS5 T11 with m units of F3 flux that is on the 3 cycle, and then some 5-form flux. So famously, when n is a multiple of m, there's a cascade, which we can relate to n=1 super Yang-Mill. Okay. The gauge theory, in this case, admits a 0-form discrete symmetry and a 1-form discrete symmetry. And the 0 form is just coming from the leftover U1R symmetry because of the ABJ anomaly. And the discrete 1-form symmetry is the femtosymmetry, which acts on the Wilson line. Okay. So here we have a 2m because we have fermion number. This is what the 2 is. And in particular, there is an anomaly which is valid in ZM between these two guys, where A1 is a background field for the 0-form symmetry, and B, the background field for the 1-form symmetry, and this is the Pontryagin. So this example is interesting from various perspectives. And then here, what the observation is that if you gauge the 1-form symmetry, in this case, it would naively break the 0-form symmetry. However, with basically field theory methods that's been recently developed, you can recover the 0-form symmetry as a non-invertible symmetry by stacking some 3D U1 Chern-Simons to cancel the anomaly associated to the fact that you have a dynamical P2 field. Okay, so that is the case when you get the PSUM theory. So this simple example have non-invertible symmetries, invertible symmetries, and have many more structures, which hopefully I'll get to discuss later. Okay, so from the bulk point of view, as I said, we can try to analyze this from the low energy first, and then we can also try to analyze it from the string theory. From the low energy, we want to construct the action of the low energy supergravity. There is a standard kinetic term, and there is a topological term, which we can more characterize from some 6D. And the point is that when you reduce the fluctuations of the RR and remote fields, in a sense, in 5D, what you get is this action where you have various interesting Bianchi identities that you have to follow. So F2 is the flux associated to a U1R symmetry. H3 here, for example, is H3 is coming from the C2 potential from the Ramon field. And sorry, H3 is the NS vector, and F3 is coming from the Ramon field. And this G2, which is appearing here, is coming from fluctuations of the 5-form due to the fact that we have 3-form flux for F. There is quite a bit of detail, but that's not super relevant. The part that's interesting here is if I solve the Bianchi identity, what I observe from the supergravity is some Stickelberg mechanism, right? For G2, you have some U1 field and then some U1 0-form field, which Stickelberg's the B2 potential. And then there is the F1, which is Stickelberging the U1R symmetry, gauge symmetry in the bulk. So you're left with a Z2M gauge symmetry. And the action, you can compute it carefully here. You have 2 pieces. This first piece is a gauge theory, which is a discrete gauge theory, which is a ZM times ZM 1 form, and then a 0 form coming from the R symmetry and its dual is essentially expressing this with a BF theory. The second term here, which is the interaction in this topological theory, exactly captures the anomaly that I need between these two symmetries. And the key point here is the gauge field A1 and B2 correspond to the discrete gauge symmetry that we want from the Stuckelberg mechanism. Their boundary values correspond to the background fields in the field theory.
Sorry, how did we get the G2 squared? We got that from the Massimino term, the integral line of.
This,
There it is. Okay, thanks.
right? In a sense, this combined terms is what gives me that. Right?
You code this n equals 1 Yang-Mills, but there's other ways to find bulk duals of something that I can call n equals 1.
Of
For
course.
instance, I can use an internal space which is S5, and then none of these features will arise. Do you have any?
I haven't studied that specific thing, but if I call it the bulk dual of n equal to 1, I should recover some of it. I haven't explored that specifically.
Well, I'm asking, I guess, that the UV completion of the theory may affect this analysis, right? If you do like n equals 1 star, for instance, or
No, of course.
5 branes on a 2 sphere, all of these things will give you some kind of n equals 1 Yang-Mills.
Yeah, so this is a case where I can see this DQFT appear in the bulk, right? In fact, this theory, I mean, in a sense, I'm cheating a bit, right? Because if I flow all the way down to the IR, I know all of this gets spontaneously broken except for the fermion number, right? So here, like, I'm really doing the analysis very close to the boundary. And in fact, this is where I can think about theory that. Okay. You could have asked me a similar question here, because here I'm focusing on this discrete part. There is also the baryon number, which is hidden here. And it's hidden here because here there is a C2 hat versus the C2, and there's an N versus an M. And it's simply the fact that you get from the Chern-Simons term of M theory, you get the B, anything associated with B2 is being Stuckelberg down. And that's with the C2 potential. But buried in this thing is also a new connection coming from the 5 form. And the conjugate of that is a U1, and that is a baryonic symmetry, which I'm ignoring. So all of those data you can see if you wish. And that is good. So let's analyze this point, right? Let's think about the discrete zero form symmetry. We can compute the Gauss law, it's straightforward to do. And the particular thing you observe when you compute the Gauss law, there is a B2 sitting here, which is valued in the ZM. This is due to the one form symmetry that is present. So you cannot immediately express the phase charge here, of course. But what you can do is this exponential of B2 squared, you can actually rewrite it as a path integral of some Chern-Simons theory that's coupled to it. Okay. And when you can do that, then instead of just trying to pull a derivative here, you can just tack the C3 term, which is the original phase charge, but then you're forced to have it with this piece, okay? So quite explicitly, you can see just by trying to construct a phase charge or an operator of the phase charge that is gauge invariant and well-defined, you're forced to have this term. And here, if you multiply these two, you do get the non-invertible feature, where this is an operator that just measures flux lines of a particular. Okay. So this is how we see from the phase charge how things come.
Sorry, could you repeat on the boundary, which is the non-invertible symmetry?
I will get to that point. Yeah. So far I'm just doing the bulk analysis of this, and then we'll get to the boundary. Yes.
I have an even more embarrassing question. What's a page charge?
It was defined. It's just the antiderivative of the Gauss law.
Okay.
Why is it a charge?
It has nothing to do with, well, never mind, I won't worry about the.
Okay. Oh, the page, well, there, I can give you two answers why page. Because the first paper I understood was written by Don Page. But also it's a page charge because it's a charge at a constant, it's a charge associated to the action of the gauge symmetry at a constant time slice. So it's a page charge.
Okay.
Depending who you are, you can take one of the interpretations. Yeah, so we have to ask Paige, what is the right naming? Okay, so let's go.
Normally something where the current is not gauge invariant, but the integral is.
Yes, that's right. But that's effectively what ends up happening, because that's the example that I have, that when I write P, it's not gauge invariant, but you can have a current.
And you'll discuss the Brane interpretation of this.
Yeah, so let me, but first, let me ask one question, which is, what is happening in the field theory? So in the field theory, let's consider the two cases, the two extreme cases. This is more or less taking M to be prime. There are other choices, but let's take these two nice choices. First, let's say the case where we have an SUM gauge theory. In this case, our boundary condition is we fix A1 and B to the boundary. So this gives me that I have the zero form symmetry and the one form symmetry, the standard in the SUM superpiano. So we're picking a global form for the gauge group. So we sum over the other field, the C2 and B and C3. And in particular, in this case, B is a fixed value, it's a constant, right? It's not something that I'm summed over. So I can just integrate out this fictitious field A that I introduced. And what I get is just a phase, which I can normalize away. And this operator is indeed invertible. On the other case, if I were to take the PSUM theory, I sum over A1 and the dual associated to B2. In this case, I have to be careful with, I'm summing over B and C, and I have to be careful with B. I cannot, because now it's also, from this point of view, dynamical all the way to the boundary, I cannot integrate it out. And the operator that I should consider in the boundary is the full operator, which is non-invertible. So this is the point that in the bulk, I just construct one thing, which is universally there, and it's universally non-invertible from the bulk. But the choices of boundary condition is what sort of simplifies it one way or another.
And since the boundary is not really ADS, strictly speaking, should we be worried about these boundary conditions for the fields that are?
I do not see why I should immediately worry about that.
I don't know.
Yeah,
because one should usually be more careful about local operators and.
Yeah, no. So this is true. Certainly, if I try, certainly, like in trying to understand some of these things and these symmetries in the cartoon that I showed earlier, like already a case that I know if I start to take n to be finite, I have to be very careful. So I'm working, in this case, I don't think at least I haven't had any issues. That's why I'm working in examples, right? I can't make an absolute general statement, so I'm working in examples. That's a useful perspective. Good. So going now, from now I can just go ahead and compute all of these generated in the bulk for each of the different gauge symmetries. And this is the one that I've just talked about at hand. So this is the Wilson line associated to A. This is the Wilson line associated to B. There's also another two-dimensional operator, which also has some interesting structure that is coming here. So the question now, when we go to the bulk, we want to understand the branes that do this so we can chase those branes. So let's do that for a moment. So if we look at this operator, so I call it N and I call it the unit 1 operator, there is a C3 which is generating it. So the thing that I want to know is go back up the ladder and ask, where did this thing come from? And how can I reconstruct it from the Ramon vector, and what is it coupling to it in an appropriate way? So you can obtain this in actually more than one way. If I look at what's the minor term of the D5, which has some Chen-Patten field, and I take the D5, which is evaluated on sigma 3 times the tree sphere of T11, this thing recovers exactly this action, with A being the Chen-Patten field. Another useful perspective, which is going to come to play later, is I can also take a D7 that fully wraps the T11, but here I allow for a non-trivial flux on the D7 along the 2 sphere. Integrating that out should go back to the D5, and then the A field gives me this here. So in a very straightforward way, you somehow doing this trick in the low energy supergravity seem to know something about the branes that I should associate them with.
But the important thing about the brane is the gauge field that lives on the
Yeah.
brane. And do the other fields play any role?
Well, they do, right? Because these are flux backgrounds that are
In the brane
non-trivial.
action, like the fermions.
No, I haven't analyzed that, so I don't know what role they play. So I'm just looking at the bosonic perspective. Yeah, that's a good question. Good. So then you could ask, so here I put the unit 1 operator. I can have unit P operator, which is where P is given mod M, mod 2M for the zero form symmetry. You can get this in a couple of ways. You can take a stack of P5 brane, right? And then it turns out if I take a stack of P5 brane, the piece that realizes the actual topological operator is the center mass mode, okay? Or equivalently, that center of mass mode, I can describe it by taking a single 7 brane, but P units of world volume flux. So both of these things seem to describe a general D unit operator.
But maybe the 7 ring would also couple to additional gauge field and so on, but all those become trivial in this low energy theory, or?
Yeah, so you can compute it explicitly in C. And this is important for what the algebra looks like, and I will say something about that. So then you can go ahead and then for each one of these symmetries, you can construct, for each one of these things, you can go ahead and construct the actual brane setup that gives you who Wessamino terms generates this. So the D5 we discussed here, for example, this operator is coming from a bound state of a D3, D1, and so on. There is this funny one where the D3 is seemed to be wrapping the hop space, but there is an interpretation of that which is more appropriate that I'll also say.
And in the cases where you don't keep the gauge field up there, that means because the gauge field is completely integrated out already in the bulk.
Yeah. Okay, good. So let me have a brief interlude to just say what this is, what is something interesting that's going on related to one's question earlier. So let's forget about holography and just see what's happening here. So if we think about this spectrum of UV to IR, at low energy we have some supergravity, and we can just write it. And there's some gauge theory that's sitting there. We can use the Gauss law to compute all the symmetries. So you can use the Gauss law and define all sorts of symmetry operators, which are going to be topological because we just exponentiated. But in the string theory, all the way up here, where we expect to have a gravity, there's no global symmetry, so something should trivialize all of these topological operators. And in particular, the observation here is that, the naive observation is that I look at these Gauss law operators that I can construct, and then the thing that appears on top is the D-brane, and simply the difference between that from this point of view is somewhere along the way, a finite tension term is generated. Okay, so a finite tension term gets generated, and because of that finite tension term, these operators that I start down here are not topological up here, which is a very curious thing, something that we're trying to think about and understand. And more broadly, it sort of raises the question, is this really an opportunity to understand something about symmetry breaking due to gravity? Or more excitingly, if I take some low energy gauge theory with some highly non-trivial topological sector, does that full sector uplift to some set of operators in the gravitational theory?
I have expected that this symmetry would be gauged in the bulk.
There's two choices. They either are gauged in which case they get completely trivialized and they disappear, or they could be broken. So this,
But if it was a symmetry, if it was something that was a symmetry in the boundary theory, right?
so
Broken a possibility. Okay, sorry. Yes.
I was ready for that. This is just a statement of something that I can think about in supergravity in general. Not even in a sense, in holography, you're seeing this play out because the operator is dynamical if we think of it as a brane, and it only looks topological because the tension is renormalized away near the boundary, right? But the phase charge, it always looks topological. So this is an interesting question which we're exploring, and hopefully we'll have something to say about it soon. So back to the business at hand. So now let's try to understand, so there is this sort of dictionary that we have from the phase charge to the branes into the operator in the boundary. Can we say a little bit more like the fusion rules that we should expect to happen? And is there a sort of is there a way to understand it in the bulk quite straightforwardly? So let's take the simplest. We take two of these operators that are non-invertible and I multiply them. So this is a field theory analysis. When you do it in general, you will get the operator with 2 units of charge. But in general, when I take these topological operators and I multiply them, you get coefficients. So these are like the typical coefficient when you multiply to operate in some group. But in general, these coefficients are actually valued in some TQFT. They're TQFT coefficients. They don't couple to anything with the physics of the bulk of the system that I'm looking at, but they're just some TQFT coefficients, and it's important to keep in mind that those things are. So this is a statement about topological operators that I've written here, where all of these things are defined in so. In the bulk, however, they come to life in interesting ways. So when I stack the 2 D5s, this thing here, you can understand, we can calculate this action as coming from a single 7-brane, but with 2 units of world volume flux. So what is happening here, this is a case where you take the 2 D5 together, because there is a 5-form flux of the full T11, the D5 basically puff up on the sphere. And then this is how you get a single 7-brane, but with 2 units of charge in the thing. So from this point of view, and then you can ask, what about this TQFT coefficients in the field theory that does nothing, but it has to be there. So this is a decoupled TQFT, which is a Chern-Simon theory. This is related to the minimal TQFT that carry some anomalies that were characterized by Nadi and Otat and Cosine. This also has the life in the bulk. In the bulk, it corresponds to the relative dynamics of the brane. You can show that this part of the action, this part of this emerges from the relative dynamics of the 2 branes that I'm bringing together. So this rather topological fusion rule, it seems to be emerging from very dynamical processes like the Meyer's effect in the bulk of in the ADS bulk. So you can then proceed, then ask, what about the fact that if I take the N operator and I multiply it, as we've just discussed already, is a non-invertible operator, you get some of U lines. Roughly this relation, if you see it, what it looks like is you should take a D5 and an anti-D5, and you should get some D3s.
Can you remind me, does the Meyer's effect rely on supersymmetry?
No. So this other part is one that we also thought was interesting. If we take the D5 anti-D5, we want to think about the Chen-Patten bundle that lives on them. And there is a choice to be made here. And in general, there's a tachyon between these 2 systems that is a section of some line bundle, which is the difference of the 2. And there's a choice to be made. So if you now want to think about this problem, when you take the D and anti-D, the Wess-Zumino term is actually known and worked out in the past for the D anti-D brane system. And you can expand it. There's a bit of work to expand it appropriately. And in general, what you get is a term, which is the Chern character of this extra line bundle that you have. And when you choose it in an appropriate way, or the value that it needs to be, depending on how the branes are set up, you get the West-Sabino term of the lower brane. Right? So this is the way you can, how you might guess a D5, anti-D5, reduce it to something within the brane. And then here, you pick L has to be picked so that the D3 that you have is localized in some useful way on the base of the S2. Where the sigma 2 is along the external time. So we try to draw this picture where this is the internal space and this is the external. So you get some smaller things that are around. The D, so you can find what you can understand what is the actual bundle that you need to put to get this effect to actually work out. And what you get is this condensation, which is going to be a sum of D3s that form some network in the original 3D operator that you had. And you can compute this. So these D3s that are actually giving you this network are themselves interesting, because naively, if you go back and look at the holonomy of these D3, they're coupled to B2, which is an NS-NS field, right? So you can ask, why do I get D3 whose coupling is to an NS-NS field? It turns out here that because you have a tree-form flux on the tree sphere, if you compute the C2 potential on the two sphere that live there, there's a non-trivial C2 potential. And what you actually end up getting is a dual Myers effect for string. Right? So it's a string in the bulk that undergoes a dual Myers effect on the sphere, which is the base of the tree sphere. And then you can see the Myers effect again coming in to describe what you're happening. Okay. So there are also the phenomena of what happens when you take a non-invertible operator and you take a charge operator and move it past, it drags a line of various kind, and that's understood in field theory. So that maps to a phenomena where we take the D5, we have an O operator that ends, and it would end on some tooth line in the boundary. And then if you drag it past the D5, you pull a string. And then if you push this to the boundary, it exactly reproduces this phenomena of charge operators passing through non-invertible symmetry and dragging the line. This is in Ising model, this is the disorder line that you would generate because of that. And this, in the bulk, is the Hanani-Witten effect playing out here. Good. So you can go ahead and just start checking. So you can, have very exciting students, so they can go and check full fusion rules and map them to strings, to some string dynamics. And in general, the intuition of why all this works is if I take one of these operators that I can construct, you can see what's happening, right? So there's a leading term always, which is what defines the charge. In this case, its leading term corresponds to some D3, D1 charge. But then you have some, in this case, for example, you have a BF action, which is coupled to the holonomies of A and B here. So this term, you can understand actually as corresponding to a set of induced D1 strings, right? If you go back in the string theory, you can ask, where is this term coming from? This is coming from an induced D1 string that are being summed over in a particular way. And this term B2 is coming from some induced F1 string that live on the operator, right? So using now this logic, you can proceed, so that's one statement. And then you also make an observation, because this is a BF theory, it's a TQFT, this operator itself has some global symmetry that lives on it, okay? So it has a global symmetry that lives on it. And you can ask what happens now if I start gauging that global symmetry that lives on it. And what that does, it generates additional operators, right? And in fact, the gauging here can be quite interesting. You can take the operator and fully gauge the symmetry. This will give you some other operator where the symmetry is gauged. You can also take the operator and do what's called higher gauging, where you pick some codimension line and gauge the symmetry along this codimension. Okay, so this is what's usually called higher gauging by Shuhang, Sahand, and other people who work on it. So this is an analysis you can do field theory. You can do a higher gauging where you gauge along the line, you get some defect on top of the defect, and then you further gauge even more. And by doing this, having interesting group, you can either gauge any subgroup, play this game, so you get a huge set of operators that is almost like turtles all the way down. And those things are actually needed to complete this higher fusion category that's supposed to characterize the symmetry structure.
Is there a picture for that in the bulk? I mean, does that correspond to
Good.
extra?
So in the bulk, this is a phenomena of branes within branes. It's a phenomena of branes within branes. So there is this project that I have with my couple of students, which is, can we really fully compile a higher fusion category from the bulk using ADS-CFT? It's an interesting thing to see whether you can actually do, right? It just tells you that somehow the physics of the branes knows a lot more about this in holography and so on. Okay, so in this talk, we describe how to realize this generalized symmetries, topological symmetries, and all of their cool properties just from the holographic perspective. We try to be somewhat systematic, but the interesting here is the thing to realize is aspects of topological symmetries, it just tells you somehow studying branes should allow me to understand more about them, right? So there is something a bit retrospective about this that you know, doing string theory continues to be very productive in interesting ways. And most of the calculations, people who are really responsible for this were these two grad students at Hopkins that are quite excellent. I'll stop here.
All right, do we have any questions?
Can I ask one more? Namely, this, aligned to enable, this analysis didn't seem to rely on n=1 supersymmetry. So if you can imagine adding some supersymmetry breaking term in the bulk,
Yep,
this will seem to go through.
that's right, because we're looking at topological
So
symmetry.
just using the internal space and in essence don't care too much what's happening.
Yeah, but it's the same thing in a field theory. I can take a field theory with some interesting symmetry structure. If I do any deformation that preserves it, all the rules follow in this, and we use this a lot. Yeah, so all of those statements should work. Okay.
You know, it's fun.
I expected it, sure.
If I take in a fusion K category, if in a fusion, higher fusion category, I take a product of K morphisms, it should be expressed in terms of K morphisms, not N morphisms where N is not equal to K.
Yes. I haven't worked this out in detail in VR. I don't want to give an answer. Once we have an answer, I'll tell you. But there's also just the question of what is a higher fusion category for which there isn't a uniformly agreed upon thing.
Oh, well. I mean, that's even true about a higher category. Are you talking about, you know, strict versus non-strict and all that nonsense?
Yeah. So we're working with a definition in Davide and Theo's paper, and we seem to be compiling appropriately. But the other thing that we, like, the reason why I sort of set out this project is to really like test this thing. Is it really true? We should expect to have all of these high fusion category, and can we work out one example A to Z and see all of these features? This hasn't been done yet. I haven't seen an example where actually this has been done anywhere. So if we complete here, this would be the first example, and then you can ask me these questions again.
Well, 2 dimensions.
Higher fusion category, higher, determine higher. Yeah. Go ahead.
I have a more basic question. With the bulk branes,
Yeah.
are they purely topological in the sense I don't have to worry about back reaction at all?
They're not topological.
Okay, but then don't I have to worry about, like, if I insert a dynamical, the bulk it back reacts and I have to address it if I'm
Good,
making.
good. And this was a statement that I'm doing this analysis very close to the boundary.
Oh, wow. So you're really leveraging the close to the boundary a lot here.
Yeah. Yes.
Because, okay, I see.
Yeah. So I can make, so that I'm able to at least keep track. For example, this set of Klebanow-Strauss, meaning this thing flows highly non-trivially and becomes something entirely different in the deep in the bulk.
And you don't have any, like, and if I try and do this in a theory that I do have like a well-defined infrared, your statement is that you have no idea what these operators will flow to naively.
That's right. That's right. But that's related to the fact that the bulk, we know that they shouldn't have topological operators. But you could still have some, I mean, but like even in the case that I said where this thing flows, I have these operators that are constructed in the deep IR, they become domain walls, right? So it's not like they disappear and just magically not show up. They become something else. So in the case of this operator that was measured T charge, in the deep IR, the symmetry is spontaneously broken. These become the domain walls. And there's indeed dynamics on them, and as there should be.
So it's been a while, but there were no shuffles to the scale goes on forever, no? So how do you do this? How do you approach the boundary if you think that you approach the boundary, but then you have to do them?
Yeah, so again, the analysis that I'm doing in the supergravity is close to the boundary. I haven't tried to go to the cascade, and that was related to Aiden's question.
You've been, no?
It keeps on going.
Keeps on going.
Yeah,
There's a log out.
yeah, no, of course, I have to import the cutoff, yeah. Yeah, the cascade does keep going, but
I don't really know why any part. The metric boundary isn't quite ADS like, but it's very close.
Mhm.
And the sort of things you're doing could,
near the boundary, yeah,
even though it's not quite ADS.
yes. But yes, that's correct. Which is have been my party lines so far. Any more questions? Well, thank you so much.